So today we will continue talking about limits. All right. I'm actually going to skip past the couple pages in the notes here at the moment. So I'm going to go ahead and skip to page 59. What I'm skipping over is just a description of limits that are at infinity, so as x goes to infinity, or x goes to minus infinity. And all that basically is just describing how we can use this limit notation to describe the asymptotic behavior of a function. Horizontal asymptotes and all that. So we'll come back to that once it happens to us. But today I'm a little bit behind, so I think I'm just going to forge ahead here and just go full bore into limit calculation. And so here we're finally getting into some problems that, much like the graphical ones last time, would be test appropriate. Let's see here. So here we go. Let's start with the so-called limit laws. These are in section page 59. I'm going to write some of them up here. All right. Here we go. And so number one, the limit as x approaches a of f of x is unique. That's what number one is saying. It's saying that if the limit exists and it's equal to two different things, they must be the same thing. So the limit's unique. Number two says that if the limit as x goes to a of f of x equals to L sub f, and the limit as x goes to a of g of x is equal to L sub g, then the limit as x goes to a of f of x plus g of x is equal to L sub f plus L sub g. So in other words, what number two says is that the limit of a sum is the sum of the limits, provided that they both exist. Three says that the limit as x goes to a of a constant times f of x is equal to that constant times the limit as x goes to a of f of x. All right. Of course, supposing that that limit exists. So you can pull constants out of a limit. All right. 4 I won't write out, but 4 says that basically items 2 and 3 extend over finite linear combinations. So like item 4 says you can keep doing this, more of the same. All right. 5 says that the limit of the product is the product of the limits again, assuming what? This presupposes that both the limit of f of x and the limit of g of x are known to exist. All right? If that's the case, the limit of the product is the, yep.
What was 4 again?
4 is in the notes. I'm not going to write it out, but it's basically it's a linear extension of. So it's like that.
Yeah, but they are in the text, right?
Yes. So yeah, this is theorem 2.3.1. Let's see here. What else do we know? 6. the limit of a composite. So if the limit as x goes to a of f of x is equal to L1, and the limit as y goes to L1 of g of y is equal to L2, then the limit as x goes to a of f of g of x is equal to L2. So the limit of the composite is just what you'd expect, right? And then number 7, the limit of a quotient, guess what? It's the quotient of the limits. Again, supposing what? You know, limits exist. And the limit. What do we need to know about the limit as x goes to a of g of x in order to make this rule? It's not equal to what? If you're going to, yeah, not equal to 0, right? Otherwise, we certainly couldn't divide by it. And then 8, substitution rule, sometimes helpful. The limit as x goes to a of f of x is equal to L sub f. Oh, excuse me, I've gotten mixed up here. Limit of limit of f of x is equal to the limit as h goes to 0 of f of a plus h. Moreover, either both of these limits exist or they both don't exist. So this is a substitution, all right? All right, there's one thing I prove in pretty much every Calculus 1 class I ever teach. The question, or? No? Okay. So the proof of some of these is pretty easy. The proof of 5 is actually pretty difficult. I think I've included it in the appendix. But I'm going to go ahead and prove number 2 because it's relatively easy, okay? So I'm going to give you a proof of 2. All right, so we're going to assume that the limit as x goes to a of f of x is equal to L sub f, and the limit as x goes to a of g of x is equal to L sub g. All right? So, great, that's my starting point. Let epsilon be greater than 0. And then observe, we may select delta sub f and delta sub g greater than 0 such that 0 less than f value of x minus a less than delta f implies the epsilon value of f of x minus L sub f is less than epsilon over 2. Why can I do this? Well, I can do this because I'm assuming the limit exists, right? That means I can get close enough to the limiting value to make the distance between f of x and L sub f as small as I like. Certainly, I can make it within epsilon over 2 units. And see, I can do the same for the g. Right? Okay. You're like, well, okay, why are you doing this? Well, let's see. All right, so choose then delta to be the minimum of the delta f and the delta g. That means that if I assume that we're within delta units of A, I get both the delta f condition and the delta g condition. 0 less than absolute value of x minus a less than delta, then this and this both hold, right? Because delta is less than or equal to delta sub f, and delta is less than or equal to delta sub g, right? Hence, for such x, consider the absolute value of f of x plus g of x minus L sub f plus L sub g, parentheses here. Let me just rearrange that a bit. That's equal to absolute value of f of x minus L sub f plus g of x minus L sub g. So now here we use what's called the triangle inequality, all right? Triangle inequality says that this is less than or equal to the absolute value of f of x minus L sub f plus the absolute value of g of x minus L sub g. Because what's the triangle inequality say? Like generically, it's absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. That's the triangle inequality. I'm applying that here, thinking of this as being a and thinking of that as being b, all right? So just triangle inequality. Now, what's the game I'm playing? I'm assuming x is within delta units of a, right? And that means I have control over how far f of x is from L sub f and how far g of x is from L sub g. Epsilon over 2 from L sub f, epsilon over 2 from L sub g. So this is less than or equal to, actually less than epsilon over 2 plus epsilon over 2, also known as epsilon, and we're done. See, we have now shown that for each epsilon greater than 0, there exists a delta greater than 0, for which, whenever we're within delta units of the limit point, the distance from f of x plus g of x to L sub f plus L sub g is less than epsilon units. So by the definition of limits, I can conclude limit as x goes to a of f of x plus g of x is equal to L sub f plus L sub g. Which again, that is what 2 is, right? What's the other way you could like write 2? Like, I know this L sub f and L sub g kind of like, I don't, it's good for the proof, it like saves a lot of writing, but don't get lost in what I'm saying. I'm saying that the limit of f of x plus g of x is equal to the limit as x goes to a of f of x plus the limit as x goes to a, right, of g of x. That's what this limit law is saying. The limit of a sum is the sum of limits. This is the proof, all right? All right, so there it is. So that brings us to theorem 2.3.2, which is on limits of elementary functions. All right? So, read along with me there. I'll let you read along here. So if we look at the limits of elementary functions, what does that theorem say? Wait a minute. Do you have it? Have you printed chapter 2? Oh, see, this doesn't work unless you guys print out the chapter 2.
Is this the chapter 2? No, it was chapter 1.
Yeah, I gave you chapter 1. I told you guys you had to print chapter 2. See, I knew I said it. All right, well, anyway, we will go ahead. I'm going to, are we good? Can you, no?
I'm sorry.
All right. Well, I guess I'll start writing limit. I'll start writing theorem 3.3.2 over here. So the next theorem I'm writing, what I'm basically writing down here, guys, is that the next kind of step in the game here is that the limit of like elementary functions is just what you kind of expect it to be. We already proved last class the limit as x goes to a of x is equal to a. That was like my first proof, right? The delta equal to epsilon 1. The limit of a constant is equal to a constant. That's the one I was talking about where you said delta equal to 1. You can make delta equal to 1 to prove that. But anyway, the limit of x to the n as x approaches a is a to the n. If we have a polynomial, p of x is a to the n, x to the n, plus plus a2 x squared plus a1x plus a0. All right? Then
You said you put 1, plug in 1 to number 2, and it would work there.
oh, okay. I'll
I mean, no, I get what you're saying, but like, beyond
but do you?
C,
Are you sure?
it being C.
Are you sure you understand? Let's see here. So what I'm saying is if you let epsilon be greater than 0, you can choose delta equal to 1. You can make delta whatever you want, actually. Then the absolute value of x minus a less than delta, right, gives absolute value of c minus c, right? That's f of x minus l. In this case, f of x is equal to c, and l is equal to c. So that's c minus c. Well, c minus c is 0.
So that 1 would be a fact.
It actually has nothing to do with it. Like, you can prove the limit of a constant is a constant. It doesn't even matter what delta is. It's just almost trivially true, sorting through the definition. For any epsilon greater than 0, I have the distance between f of x and l, which is c and c, is less than epsilon. So therefore, this.
Could you pick any number for delta and it do the same thing?
Yeah, 42, 23, whatever floats your boat. Just not a negative number, not 0. So, like, if you look at number 1, number 2, and number 3 here, what I'm saying is you can just plug in the limiting value to calculate the limit in those cases, right? Limit of x goes to a of x is a. The limit of a constant is the constant. For x to the power n, like the limit as x goes to a to the n. You have a polynomial, right? A weighted sum of powers of x. Take the limit as x goes to a, guess what you get? Oops, I'll write over here. Then the limit as x goes to a of p of x is just p of a, which is to say, I just plug in x equals to a up here. So limits of polynomials are easy. You just plug in the limit point, and that's all there is to it. Right? Yep.
What's that symbol in the maps there? Beside that.
The symbol in the
Yeah, in the caps.
here?
Yeah.
Oh, yeah.
Down.
That one. What's that?
Oh, this.
Yeah.
That's supposed to be 0. I'm saying if n is either a whole number or 0. So basically x to a non-negative power, like x, x squared, x cubed, x to the 20th, whatever. 5, if a is not equal to 0, then the limit as x goes to a of 1 over x is equal to 1 over a. You just plug it in. All right? Square root, what do you think happens? If you can see where I'm going with this. The limit as x goes to 0, x goes to a of the square root of x is equal to the square root of a for a greater than 0. Now, at 0, we can only approach from the right, like we talked about last class, right? But as long as you're not, if for positive a, you can look at the double-sided limit for square root of x, and it is exactly what you'd kind of think it would be. All right, so I also have a 7 and an 8, all right? So basically, let me just summarize what 7 and 8 say. 7 and 8 say, guess what? You can take any algebraic expression and calculate the limit of it just by plugging in the value at the limit point, just plugging in the limit point a, provided that the formula defining the function makes sense at the point. All right? So an example of 7 and 8, well, let me just finish this theorem here. So that's 7 and 8, which I'll let you read, but I'm not going to write out. Then there's 9. 9 says that the limit of sine and cosine limit of cosine of x as x approaches a is just cosine of a. And likewise, the limit as x goes to a of sine of x is equal to the sine of a. All right? And then number 10, I have the limit as x goes to a of b to the power x is equal to b to the a. Here b is greater than 0. So number 10 says that the limit of an exponential function you can just get by evaluating at the limit point. So let me just, yeah?
It's just like a coalition between x and a, just normally. Just if you see x, just think a.
Plug in a. Now I've stated it in terms of a, but often in problems a will be a specific number or something, right? But yeah.
But if it's understood as a, you can figure out the problem there.
Well, yeah, I think
Specifically a, but
the overarching moral of the story I'm telling here is simply this. If you're calculating the limit of an expression, and that expression is well defined in terms of regular rules of arithmetic, at the limit point, you can just plug in the limiting value. That's all there is to it. Now, to actually prove those things in terms of epsilons and deltas, it would take me 3 weeks. I mean, it can be done, but it is technical. It's difficult. And of course, I mean, you can see how to kind of go from here, right? If you have the limit of cosine, right, and you know that the limit of the reciprocal is just 1 over the thing, and you've got the composite rule, you could put those together to do something like the limit of secant, because it's just 1 over cosine, right? I mean, all right. You're like, so it can't all possibly just be this easy, right? Because I really haven't, what have I said? I've said it works just like algebra up to this point, is what I've really said. All right? So what's the rub? One more easy example. And this one's not in the notes, I'll just add it. Say the limit as x goes to 7 of the cube root of x squared plus 1 over x plus the sine of x squared plus e to the x equals. This is a very silly example, but I think it serves it serves to illustrate my point. How do you calculate things like this? You just use arithmetic, essentially. I mean, and this is the first thing I try to do with any limit, is I try to just plug in the limit point and see if it works. If it works, it works. That's what the theory says. And by it works, I mean there's no division by 0, and there's no point going into a function which is outside the domain of the function, right? Like a log of a negative number, square root of a negative number. These are bad. So here we've got the cube root of 7 squared, which is 49, plus 1 over 7, right? Any problems there? Can we take the cube root of a number? Sure can, any number, no problem. Sine of x squared, what's x squared? When I plug in 7, it's 49, right? Plus e to the 7 power. That's it. End of story. Game over. Problem solved. Now, if you wanted me to break this down, we could look at that as a subsequent application of about 10 limit laws, one after the other. All right? So surely it can't just be this easy, right? So what's new? Well, here's an example. I'll call this example 1. What if we look at the limit as x goes to, let's say, 0 of sine x over x? Try plugging in the limit point into the expression. What happens? Yeah, we get, so sine of 0 over 0, which is 0 over 0. This is, undefined, right? That is not something that arithmetic allows for. So this is our first encounter of an expression that is this is said to have indeterminate form. Zero over 0, right? And I usually say indeterminate type. Type 0 over 0. Now what this word indeterminate means is that it could work out to different things. It might not exist. It might work out to infinity. It might work out to 3. it might work out to 2. Now, for a given expression, I'm not saying this is like a political decision. It depends on which party's in power as to the answer. Like, it is a specific answer for a specific expression. I'm not saying indeterminate in that sense. It's not like, well, today sine x over x worked out to 3, but yesterday it worked out to 2, you know? No, the limit as x goes to 0 of sine x over x will always and forever be 1. All right, so if you have the notes, when you look at the notes later, I have a table of values. And if you look at the table of values, see I have x going closer and closer to 0, and the values of sine x over x get closer and closer to 1.
I got you.
So like you can numerically poke values of x that are closer and closer to 0, and look at how sine x over x gets closer and closer to 1. And that's how I know, numerically, not a proof, mind you, not a proof, that the limit of sine x over x is equal to 1. Turns out it's equal to 1. I will give you a ironclad proof of this later, all right, but not today. All right, so what are the other indeterminate types, indeterminate forms? We need to recognize these because when we see these, we must deal with them. How do we deal with them? Well, we're about to see that, all right? Limit of f over g is type 0 over 0 if lim f equals to 0 and lim g is 0. It's type lim f over g is type infinity over infinity if the limit of f is infinity and the limit of g is infinity. All right. Actually, they could be plus or minus infinity. It doesn't really matter. One could be infinity, one could be minus infinity. We don't care about all that. In this thinking, it could be plus or minus infinity, actually. Okay? 3. Another kind of pattern you got to watch out for, the limit of a product is type 0 times infinity, all right? If the limit of f is what? 0, and the limit of g is infinity. I should be careful. Plus or minus infinity. It doesn't matter if it goes to plus or minus. All right. And the fourth common indeterminate form is when f minus g is type infinity minus infinity. All right? And when is that? That's if the limit of f is infinity and the limit of g is infinity. All right. There I do need the sign of the infinities to differ in order to have the ambiguity. Like, all right. So now, finally, we get to do some examples that require some algebra.
Is that 0 of infinity or number 3?
Number 3. 0 times infinity. I think in the notes I just have 0 infinity, but it's really like times infinity. So these are the basic indeterminate forms. There are also indeterminate powers. We'll eventually talk about those, but so if the limit you're looking at is indeterminate, what that means is you need to find some method of argument to remove that indeterminacy. That really is, another word you could use would be ambiguity. To remove the ambiguity to find what the limit works out to. This can be very simple, or it can require deep analytical methods. Like example 1, to prove that that's 1, not just using a numerical method, it's really kind of a pain. Example 2. All right, let's try it out here. The limit as x goes to 2, all right, here we go, of x squared minus 4 divided by x minus 2. So, sidebar. First thing you do, think about plugging in the number, right? Maybe a good practice is to go like over here and go, okay, I'm going to try plugging in the number into the limit, the expression, which is being limited, rather. And, when I do that, what do I get? I get, oops, that's 4 minus 4 over 0. That's 0 over 0. This is type 0 over 0. Right? So what do? The answer? Algebra. Yeah? So we go, okay, well that's the limit as x goes to 2 of x minus 2 times x plus 2, right? Because we can factor the numerator. Now, when can I cancel x minus 2 and x minus 2? What condition is needed for that cancellation to be legitimate? You don't always think about this in algebra, but in order to make this cancellation, right, I require, since x is not equal to 2, I can do that. How do I know x is not equal to 2? This expression is inside the limit, right? We've defined the limit precisely such that we consider values close to 2, but not equal to 2 itself. So that algebraic step is completely legitimate inside the limit. Right? And what does it leave us with? Well, 1. I didn't really need to write that, but at which point I go, happy day. I can just plug in my stuff. I can just plug in 2. What do I got? I got 4, right? 2 plus 2, 4. So after we do algebra, this algebra step removed the indeterminacy and left us with a limit which we could just straight calculate. All right? Yeah, go for it. You're fine. Just be wary of my cord. I've almost tripped on it already. Oh, by the way, that was ICE 2.3.6. Sorry. Shall we do another? So ICE 2.3.7, let's look at the limit as x goes to, let's say, 3 of x plus 3 over x squared minus 9. I'll make our life a little bit easier. I'm gonna put a plus here. So we can have have a slightly easier example. So guys, what do you, 6, so yeah, when I plug it in, I get 6 over 0. That's not an indeterminate form, all right? When you get 6 over 0, that means that thing blows up. That means that, yeah.
Yeah, I'm sorry, but when you put the plus over the 3,
Ah,
what's
yes.
the difference?
So what this means is as you think about the number line, right? The limit points 3. So we're looking at values like over here. We're approaching like that, these values. So this means we're basically thinking about evaluating expression at like x equals to, say, 3 plus a little delta. And so,
3 minus is the other way.
yeah,
2.999.
right. So like if you were going the other way, like 2.99, you'd have x equals to like 3 minus the delta, where delta is a little positive quantity. And you can think about plugging that in and seeing how it kind of all works out. Or you could think about just plugging in a number that's really close to the limit.
Yeah.
Like you said, for this one, you could think about plugging in like 3.01. What would happen? You get 6.01 on top, and downstairs you get 9 point something, 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 minus 9, so you get a very small positive quantity. So if you have 6 over a very small positive quantity, it's a very large positive number. So this would be infinity. And again, this is because values slightly larger than 3 cause x plus 3 over x squared minus 9 to look like 1 over, just 1 over, stuff over big number, right? If I have stuff over a big positive number, good grief, idiot. Exactly the opposite of what I wanted to say. Tiny positive number, tiny. Right, tiny positive number. 1 over a tiny positive number is huge, right? This is very bigly. Huge. Like the budget. I don't know, whatever. So this can happen, right? It doesn't always have to be an indeterminate form. It doesn't always have to be something you can plug in. This is the other thing that can happen. It might just blow up. Let me change this problem ever so slightly. 2.3.8. The limit as x goes to minus 3 of x plus 3 over x squared minus 9. So now I can think about plugging the limiting value, the limit point in. It gives me 0 over 0. This is type 0 over 0, right? So what can we do? Well, we can do, you guessed it, algebra, right? So what algebra are you gonna do? What should we do?
Split up x squared minus 9.
How's that factor?
Minus 3x plus 9.
Lovely. And then so now we can do what? We can cancel these guys since x is not equal to 3, right? X is not equal to minus 3 in the limit. We haven't changed the value of the limit by doing that algebra step. And so what we're left with, of course, is the limit as x goes to minus 3 of 1 over x minus 3, right? Now what happens? Well, I think we can just plug in minus 3, right? Minus 3 is minus 6, right? So we get minus 1/6. And there you go. So look, we've already seen type 0 over 0 can do what? It could be 4. Type 0 over 0 in the sine example worked out to 1. Here, type 0 over 0 worked out to negative a sixth. This is why it's called indeterminate. We can't figure out what it goes to until you resolve the ambiguity with algebra, all right? I think it's worthwhile, well, let's see here, another example here. Try to give you an example of a different type that involves kind of a different algebra skill set here in this next example. So this would be ICE 2.3.8. Here we go. The limit as x goes to 4 of 2 minus the square root of x divided by x minus 4. So what do you guys think about that? Can we just square a limit, though? No. Yeah, what happens when you plug it in? You get 0 over 0, don't you? Because we get 2 minus the square root of 4, which is 2. 2 minus 2 is 0. And downstairs we get 4 minus 4, which is 0. So, right? That's... So what are we going to do? All right, so going to have to be a little bit creative here. There's various tricks you could do, but I think the simplest thing to do is to notice that x minus 4 is x square root of x squared minus 2 squared, right? Which means it's the difference of squares. So you can rewrite this as 2 minus the square root of x divided by square root of x minus 2 times the square root of x plus 2. Now that is a pretty sneaky step, right? Yeah. Now once you do that, these two, they don't quite cancel, do they? Maybe I should make another step right here. Like I could the numerator, let me rewrite the numerator as the square root of x minus 2 with a minus factored out, right? Just to see that this and that cancel and leave me a minus 1, right? And so what do we get? We get minus 1 over the square root of 4 plus 2. Now that we can do because, negative 1/4. Let me give you some terminology for what we're doing. Definition. Now I'm going to give a better definition. I give a better definition in the notes, but I think it's worth it. I think a definition is worth giving now just for the sake of conversation and trying to make sure that we all are on the same page with what this word means. F is continuous at A in the interior, let's say, of the domain of F. Don't worry so much about this. All I'm saying is that A is a point in the interior of the domain. And the reason I'm saying that, F is continuous at x equals to A in the interior of the domain, provided that the limit as x goes to A of f of x is equal to f of A. So a continuous function is simply one that you can calculate the limit by plugging in the limit point. Our goal in all of these calculations that we've been doing is to make steps on the expression to convert it from an indeterminate type to a function, rather, which is continuous. So then we can just plug in the limit value. That's it. We try to do algebra to change the discontinuous expression into a continuous expression, if we can do that. Now, we can't always do that. Sometimes the discontinuity persists, like the indeterminate form can't be fixed, like our infinity example earlier. So continuous functions are important, right? We'll be talking about more of the, we have to talk, for a little bit about what we know about continuous functions. So we'll get to that soon. Yep.
What's those I, T,
Interior, so like the inside, away from the boundary point. It's the largest open set, which is inside the domain. So just to give you a counterexample, the square root.
Yeah.
Every positive number is in the interior of the domain, but 0 is not in the interior of the domain of square root. So like I wouldn't discuss continuity of the square root function at 0 using an interior point. That's a boundary point. So like continuity of the square root function so continuity of the square f of x equals the square root of x at 0 is judged by the following fact, that the limit as x goes to 0 from the right of the square root of x is equal to the square root of 0. So the square root function is continuous at its endpoint because that right limit, this limit, of 0 plus exists. I can't put a double-sided limit at the edges of the domain. That's what this is accounting for, just that. If I'd been smarter, I would have just not written that because I was trying to avoid talking about this, but I failed. But good for you. Curiosity, very good, very good. Where am I? ICE 2.3.8. I guess that would put us to ICE 2.3.9. Let's see here. So another example. How about 1 over t minus t squared plus t? 1 over t minus 1 over t squared plus t. And we're looking at the limit as t goes to what? Say 0. So what's happening here, if you try to plug in 0, the first thing is infinity. The second thing is infinity. So this example is one of those ones I was indicating earlier in the thing I just erased. This is type infinity minus infinity. So how do you tame one of these things? Well, pretty much you're going to make a common denominator. That's the go-to move here. So let's see here. So this is, I'll do one more step. This is 1 over t minus 1 over t times t plus 1, right? So if I look at it like that, it suggests I do the following algebra. T plus 1 minus 1 over t times t plus 1. See what I did? So I multiplied the first fraction by t plus 1 over t plus 1 so that they had a common denominator of t times t plus 1 so that I could subtract them. Which is pretty awesome because after you subtract them, the 1's cancel. And then you can reduce the t from the upstairs and the downstairs, right? So this simplifies too. Which is just wonderful because then we can do what? This now is a continuous expression in t. In the sense that I can plug t equals 0 into it and it's well defined. Right? 1 over 0 plus 1, what is that? That's 1, right? So if anybody asks you what's infinity minus infinity, you should tell them 1. I mean, you can tell them whatever you want, because you can make a limit of a type infinity minus infinity work out to whatever value you like. It's an indeterminate form. Let's see here if I can find. I don't know if I'm trying to see if I can find a type 0 times infinity one that I like for us to look at. I don't have one on hand. Yar. Well, I'm sure it'll come to us before we know it. So, all right. So that's ICE 2.3.9. All right. Next up, ICE 2.3.10. Need another example. Let's see here. Man,